All right, before we looked at um, finances, how interest affects the principal that you put in to the bank or invested in some place. And now we're going to look at, in general, a lot of applications in nature take exponential curves to increase or decrease, such as in chemistry, you have radioactive isotopes that decay. They use exponential curves. There's also some population applications in biology. And here's one of those examples right here. We have a state's population declining at a rate of 2.6% annually, and the state currently has 11 million people. If the population continues to decline, predict the population of the state in 15 and 30 years. So, what we're going to do is we're going to use a very similar equation than that we use in determining money. We're going to have um, our amount, we'll call it n, equals our initial amount, which we'll call n sub 0, meaning the amount we started with. And we're going to have 1 plus the rate to the t power. Now, this plus can change to a minus if you have a decreasing rate, like this one is declining. So we're going to use a negative at 2.6 for our rate. We also want to make sure that this matches the time unit we're putting in. Since we're dealing with annually, we want that time to be in years. So we're trying to find the number after this population declines. So we start with 11 million. So 6 zeros times 1 plus my rate is negative 2.6%, which let's divide that by 100. We want to have 0.026 for my actual rate there. And first, let's try 15. So we'll throw that into the calculator. Let's see here. 11 million times, we'll say 1 minus 0.026. And close the parentheses. That needs to go to the 15th power. I get 7 point, let's see, yeah, about 7.4 million, we'll say. I'm rounding, of course, but that's after 15 years. Now let's try 30 years. So we'll put that in 11 million times 1 plus negative 0.026 to the 30th power. Let's see what that population looks like after 30 years. So let's just second entry, bring the same thing down and change this 15 to 30. And I get, it looks like 4.99 million after 30 years. So now we're going to take a look at what happens with this same situation, but instead of annually, I notice we have it declining continuously. And as you might expect, we're going to use our constant e to figure this out. And just like with money, we use the equation PERT. Now we're going to use how the book defines it. It's exactly the same equation, only now we're using n. I will call it NERT. So we have, um, we're trying to find our uh, final population here, n, and n sub 0 is still 11 million. So I'm just going to do it twice in my calculator. Once is going to be 11 million e times my rate. And remember, it's negative 0.026 times time, which is 15. And we'll look at it, the same situation, and negative 0.026 times 30 for my time. We'll put these in my calculator. 11, 1, 2, 3, 4, 5, 6 times e to the negative 0.026 times 15. That gives me It looks like 7.4 million again, roughly, for my population. And I should use curly equal sign since it's approximation. And then let's just put that in again, e to the negative 0.26 times 30, and we get about 5.0 or 5.04 million. So that's how I would solve this problem if it is asking continuous decline or continuous growth. So now I have a couple examples for you to look at. Here we have a town increasing at a rate of 2% annually, and we want to find that population after 10 and 20 years. And then here you see we have a continuously increasing population of 2%. And again, find what that would be increasing after 10 and 20 years.